Hello, everybody. Good morning and welcome to the CMSA Colloquium. Today, we are very glad to have Professor Samir Mathur as the first speaker of the spring term. Professor Mathur is a faculty member in the High Energy Theory Group in the Department of Physics at Ohio State University. Before that, he was a faculty member at MIT and held postdoc positions here at Harvard and the Tata Institute of Fundamental Research. In this highly anticipated talk today, he will tell us about the black hole information paradox. So please.
Okay, thank you very much for the invitation to give this talk. Here is an outline of what I would be saying. So I'll begin with an elementary review of the information paradox, because I understand not everybody in the audience is a physicist. There are mathematicians as well, and also not everybody in physics works on the information paradox. But as we will see, the puzzle really arises because in a black hole, the picture we had of the black hole from classical physics was that all the matter goes to this central singularity and the rest of the space is really the vacuum. What we find in string theory, though, is that the puzzle is resolved by the fact that this classical structure is not what we get. When you actually try to make a black hole by taking a bound state of strings and branes in string theory, you actually get something which is a big ball. We just call it a fuzzball, which then basically has no horizon. It radiates from its surface like a normal piece of coal, and there is no information paradox, because the paradox really came because the radiation that Hawking found from a black hole came out of pair production from the vacuum. The vacuum has no information, so the vacuum creates pairs, there's no information. But if you really have a solid ball there of something stringy matter, then of course it's just like any ordinary object and there is no paradox. So this would have been the end of the puzzle, except that some people wanted to preserve the original picture of the black hole where you did have a vacuum around the horizon. But then you could ask, how would they solve the information puzzle? And the belief was that, well, Hawking did some leading order calculation, but there could be many subleading terms which introduce delicate correlations. So these dotted lines here indicate delicate correlations. And because so many particles are radiated by the black hole, somehow these delicate correlations might be hiding the information in some subtle way. It turns out by this theorem proved in 2009 that actually this is not possible. If you actually make small corrections to the dynamics at the horizon, then you can never actually get the information out. You prove this using some theorems in quantum entanglement entropy, quantum information theory. So you actually need a non-trivial structure at the horizon. And in string theory, every time we try to make a bound state of strings and branes, we find such a structure. In fact, the whole horizon is completely gone. And so you would think that the fuzzball structure has solved the puzzle. But in fact, some people still continue to look for alternatives to the fuzzball resolution. And if you have been following some of the physics literature in recent days, you would hear words like wormholes, quantum extremal surfaces, spacetime is built by entanglement, and so on. But actually, in these kinds of pictures, what one is trying to do is one is trying to still preserve a smooth horizon for the black hole, and then trying to argue that somehow little wormholes that connect the black hole to the far away radiation is somehow bringing out the information or somehow helping with the information puzzle. It turns out that these ideas can be ruled out by a little extension of the small correction theorem that I just mentioned. We call that the effective small correction theorem for reasons that you will see. And we put this in this paper just a few months ago in November. And so in fact, one finds that all the different ideas which are built on these concepts, this bunch of concepts actually do not work. So then you should go back and see, well, what is the fundamental reason that people were trying all these ideas, which all had different kinds of flaws, which we explored here? It turns out that there are two very basic misconceptions which are underlying this entire direction, for which reason this thing was actually not working. And we'll come and see what those reasons are. And they're in this paper, which is to appear. So in the end, I'll just come and tell you that as far as we believe, the fuzzball paradigm remains the natural resolution of the information paradox. And it's something that people should focus on, because understanding that black holes are actually fuzzballs seems to give us very interesting effects of quantum gravity on the cosmological scale, because just like a black hole has a black hole horizon, the cosmology has a cosmological horizon, and all puzzles like the cosmological constant puzzle and inflation and so on are dynamical effects at the scale of the cosmological horizon, and any new effects we find for the black hole horizon has likely effects on those scales as well. I won't have time to talk about this, but I just wanted to mention it before I start. Okay, so let's make a very first pass at the black hole information paradox. It's a very robust paradox because it is really based on very simple ideas. And the whole idea that leads to the paradox is something we all know, that gravity is an attractive force. So take a big mass capital M over here and take a test mass little m and keep it at a distance r away. Now the potential energy of this mass, just in Newtonian gravity, is minus g first mass, second mass upon the distance. And this minus sign here is what tells us that gravity is an attractive force. Now by itself, this test mass little m had an energy E equals mc square. But when you place it near this bigger mass, we also have the potential energy. So just as a rough first pass, let's say the total energy of m is the intrinsic energy mc square, and then you add the potential minus g mm over r. But then you see that if you start making r smaller and smaller, at this particular value, the net energy of m actually becomes 0. And if you make r even smaller, if you take it inside this critical radius given by this, the net energy of m would actually be negative. So that's very interesting. You can take this particle of test mass m. Normally, every particle costs you positive energy mc square. But if you place it sufficiently close to a heavy mass, its net energy is negative. So what does that mean? Of course, we should really be using general relativity for all this, because once you use special relativity, E equals mc square, and you use gravity, which we are doing, really they should combine to make general theory of relativity. But nothing changes much. You only get an extra factor of 2 in this. And if you bring something within this radius, you find that there are states with negative energy in the classical theory of gravity. Okay, so what's wrong with having a state of net negative energy? Well, in quantum mechanics, the vacuum can have fluctuations. For example, the vacuum in this room, it's not really empty. It has fluctuations where an electron and positron, like drawn here and here, can pop out of the vacuum for a short while and disappear back into the vacuum. They're just called vacuum fluctuations, and they are observed in physical phenomena like the Lamb shift. So the extra pair costs some energy, let's say delta E, and you're allowed to have this fluctuation because by the uncertainty principle, you can have a fluctuation of energy delta E as long as it lasts for a time delta t, which is shorter than the relation given by delta E times delta t is less than h bar. Well then, if these fluctuations happen near the horizon, then something different can happen because the particle inside the black hole has a net negative energy. There can be a particle outside which has a net positive energy, and the total energy of the pair this time can be 0. And then from this equation, you see the delta t can be infinity, which means the particles don't have to recombine. The state has the same energy as the original black hole. The new pair doesn't have any net cost of energy. And then the outside member just drifts off to infinity. That is what is called Hawking radiation. The inside member had net negative energy, so reduces the mass of the black hole, and so energy is conserved overall. And this is the Hawking process by which a black hole actually keeps emitting radiation and disappearing. The problem, though, has to do with entanglement. When you produce a particle pair from the vacuum, you could end up with the electron on the left and the positron on the right, or you could end up with the positron on the left and the electron on the right. In fact, you get a linear superposition of the two. This is what we call an entangled state. If you superpose two states like that, if you ask what is the state of the particle on the right, there's no answer to that. It's a positron if the other guy is an electron. It's an electron if the other guy is a positron. But that's fine. Everywhere in quantum mechanics, you find entangled states. And so what you find here is that the state of the radiation is entangled with the state of the remaining hole. So the entanglement can come from many places. Here we took the example of charge. So the positive and negative charges lead to this kind of entanglement. It could, if the particle doesn't have charge, it could just have spin, and the particles which are produced from the vacuum then have net spin 0. So if the inside particle has spin up, the outside is spin down, and then downtime up, it comes out in a singlet state. So again, they can be entangled by spin, but really in an even more fundamental sense, if the particles you're looking at are both spinless and chargeless and everything, there's still entanglement just from the occupation number. If there is no particle here, there'll be no particle here because they come out in pairs. It's a probabilistic process. And if there's one particle here, there'll be one here. If there are two here, there are two here. So you get something like this: 0 inside, 0 outside, 1 inside, 1 outside. Total quantum state, the superposition of this kind. And we call these kinds of states entangled states whenever you have two systems, here the inside of the black hole and the outside, the radiation. If the state of this is some psi I for one system times chi I for the other system, if that's the whole state, we call it a factored state or not entangled state, but there are many terms in the state, psi1 times chi1 plus psi2 times chi2. If there are two equal terms in this, we say the entanglement is log2. If there are three terms, psi1 times chi1 plus psi2 times chi2 plus psi3 times chi3, like this, the coefficient is equal, entanglement is log3, and so. So this is what we call an entangled state. And now here comes the problem. As the black hole is evaporating, the entanglement of the radiation with the inside keeps growing, because after n steps of this evaporation, the total entanglement of all this with what's left behind becomes n times log2 in the simple model that I took. So when the black hole is actually reaching the end of evaporation, we have to ask what happens. Since the black hole mass was going to zero, the simplest assumption is the black hole disappears completely. It goes back to the vacuum. That was Hawking's assumption way back in 1975. And now you have a serious problem, because this radiation quanta that you have here, they are in an entangled state. They have no state by themselves. It's entangled with something, but whatever that something was has now disappeared. So there's no state of the universe at all that you could write down. There's no pure state for this. And the whole thing can't be written as an entangled state either, because the guy it was entangled with is not there anymore. So in fact, because no state is possible for these remaining guys, we get a violation of quantum theory. And this was Hawking's claim in 1975, which made him so famous, that once you make a black hole, it will automatically evaporate. But the way it evaporates, the radiation that is left, the energy is conserved, because this energy is the same as the mass of the black hole, but no state can be assigned to that radiation. And so now we have violated quantum mechanics. People didn't like this conclusion. So what they said was, well, let's assume that when the black hole comes down to, let's say, Planck size, some quantum gravity effects that we don't know, some unknown quantum gravity effects, might stop further evaporation. So we'll be left with what is called a remnant. Well, that's okay. Then at least you've avoided the problem. These guys are entangled with whatever is inside the remnant. But the problem is that the remnant has infinitely many possible internal states. And that's because you could have started with a black hole of arbitrary large mass and then come down to Planck mass. So in fact, you would have an arbitrary number of these remnants. And then if you try to make a quantum field theory, which has an infinite number of possible states, all with a bounded mass living in a bounded volume, it turns out there are many difficulties with any such quantum theory. So in fact, there are no good solutions near the end point of evaporation. And so you have a problem. And this problem is called the black hole information paradox. Just to reiterate, the source of all the problem, as you can see, is the fact that gravity is an attractive force. So its potential energy has a negative sign. All the matter which made the black hole has gone to the center. You can see that as a central dot. And then other things fell in, all these members of the pairs that went in. So you would think there's so much stuff here. How can it disappear? But of course, the problem is because the gravitational potential energy has a negative sign, this whole thing has a net energy which is actually going to zero. The intrinsic energy of all the particles is positive, but the minus gmm over r is negative. If the net energy goes to zero, then you start wondering, why shouldn't this guy be the vacuum? Or you try to make remnants, whatever you do, there's just no states possible when there's no energy. And that's where the problem comes from. Okay, so now let's see why this problem is so hard to solve. It's such a robust problem because it's based in such simple language. Let's make a second pass at this. And in this second pass, we'll actually completely understand the technical formulation of the information paradox. So the first thing that people realized was it's very hard to prevent yourself from making a black hole. Because now here I have drawn time going upwards, and the radial direction is outwards, and then the angular direction is sort of round in a circle. So if you take a star, once it stops burning, it will start collapsing under its own gravity. At a point where it's still quite low density, it passes through its horizon radius. Far away, the light cones look like this, okay? And everything can only travel inside the light cone. But as you come closer in, the gravity turns the light cones inwards. And at this point, you can see the light cones have tipped inwards, so nothing can actually get out. That's what's called the horizon. And if you go further in, the light cones point purely inside. So everything has to keep going in. It can't even stand at one place, as you can see. And that's why all the matter rushes to a central singularity. And it forces you to have a vacuum at the horizon. That's why we keep drawing these pictures. Nothing can actually stand at the horizon. And the fact you can't put any structure at the horizon is how we got all these no-hair theorems, that black holes have to be completely a vacuum here, that there's no structure there. So firstly, you have to get a black hole, people thought. And this is at the classical level. But if you look at the semi-classical level, for the weakly coupled quantum field theories, the way we understand them, the same conclusion holds. You actually get the vacuum state there, the state of the quantum theory. And that's because the quantum field, when you expand it in modes of creation and annihilation operators, the coefficient functions there are actually the same functions that appear in the classical wave equation. So anyway, you find that the quantum theory also must have the vacuum if you're doing perturbative quantum theory. Well, then once you have the black hole and you have the vacuum around the horizon, it's very hard to avoid the Hawking effect. Now, if you're not familiar with general relativity, please don't worry because we won't be using much of it. But if you are familiar with it, this is the actual metric of the Schwarzschild black hole. And in this metric, what you see is that the time part, which normally has a minus sign, the space part, which normally has a plus sign, once you go inside the horizon r equals to m, they interchange roles. This becomes plus and this becomes minus. And the crucial point about this is that if you then look for a space-like surface outside the hole far away, a space-like surface is t equal to constant. But inside the horizon, a space-like surface is r equal to constant. So because they have interchange roles. So if you draw a complete space-like size in the entire space-time, these are what are called Newton-Finkelstein coordinates. And again, none of this will be required for understanding what I'm going to say in the colloquium. Here you have some kind of time, roughly speaking, it's called a kind of time. Outward here is the radial distance. So far away, t equal to constant, the space-like sizes look like this. But inside the horizon, space-like sizes are r equal to constant. So inside the black hole, there's actually infinite amount of space because r equal to constant, you can put r equals m. Halfway between r equals 0 and r equals to m, you can draw this line and make it as long as you like. There's an infinite amount of space inside the black hole. And if you draw these complete space-like slices to try to foliate the entire space-time, well, outside I'm trying to keep on increasing the time separation, I'm going up, but inside I can keep making the slices go like this. But we can see that what happens is space-like slices, later ones, have to be longer than the earlier ones. So in fact, the black hole space-time, even though it looks time independent when you write the metric in the Schwarzschild frame, once you actually include the outside and the inside, the complete metric, there is no foliation by slices which are all time independent. Later slices have to be longer than earlier slices. And once slices have to stretch, there's no time independent vacuum on this. And this continuous stretching of the slices is what gives rise to the Hawking pair production. We're now actually not using a cartoon trick of seeing the pairs as fluctuations. We're now actually going to see how Hawking process really arises. Stretching of slices leads to the Hawking pair creation. Let's make a one cartoon slide of how we understand quantum field theory. At every point of space, let's say in this room, we take a harmonic oscillator, just let's say a ball coupled to a spring, and then we join all these harmonic oscillators by springs, so we also couple them. So if you have a chain of coupled harmonic oscillators, that's a complete representation of a scalar field theory. So it's not an approximation. As you take the limit of all these points going to 0, you actually get the quantum field theory of a scalar field. Okay. So at each point is a harmonic oscillator, and as I said, they are coupled. Once they are coupled, you can go to the Fourier basis, decouple them, take the vacuum state of the entire chain of coupled harmonic oscillators. This is the vacuum state, and that's the actual vacuum of the quantum theory. And then if you actually act with the creation operator for one of these Fourier modes, then you excite the system, and that's one particle of that particular Fourier mode in the room, and so on. It's just a cartoon picture of what quantum field theory is. Now, how does it become relevant for the black hole? As we saw, the light cones outside are such that you can really escape. If you're outside the horizon, you can escape the thing, and that's a line like this, a light-like ray going out. But if you're inside the horizon, as we had seen, the light cones tilt inwards. So in fact, you'll just keep getting dragged in, and you can't escape that this line over here. So the whole role of the horizon is that it takes null geodesics, which were all going in the same direction, and it separates them. It peels them apart. These guys go out, and these guys go in. So any Fourier mode here actually starts stretching. And if it was in the vacuum state near the horizon, which is what we had, as the Fourier mode stretches, it becomes no longer the vacuum, and you get particles. The outside member, we call it B, the inside member, we call it C, and this is the actual pair creation. Let's see how to actually compute the state of the pair. And the toy model on this slide actually has everything you need to know to understand how Hawking's actual calculation is done. So if I take the Fourier modes on this early time slice, and I represent the inside part as this harmonic oscillator, the outside part of this harmonic oscillator, and because they are close, they are coupled. So you just take two harmonic oscillators and you put a coupling between them. Okay, so you can solve that system, and you find the vacuum O as the ground state of two coupled harmonic oscillators. But when these particles separate, when these trajectories separate, let's say these harmonic oscillators are no longer coupled, so I break them up. And then all you have to ask is, if you start with the ground state of two coupled oscillators, and then you remove the coupling between them, what state do you end up with? You do not end up with the state which is the vacuum for the first oscillator, vacuum for the second. You have a bit of that state, but superposed with that, you have the state which has one excitation here and one excitation here, plus something with 2 and 2, and so on. And there you see the entanglement. You don't have to worry about all the rest of it. It's just, you can just see the entanglement there. And this here, this slide here actually gives you, it looks like a cartoon picture, but actually the entire derivation of the Hawking's effect is right here. So if you go to the actual full calculation, you can reduce it down to what is here with no loss of generality. So all that's going to happen is you'll have not two oscillators, but more oscillators. You can couple them, but roughly speaking, you can break it down to two oscillators of the kind of frequency you want. And so coupled harmonic oscillators becoming decoupled because trajectories separate at the horizon is the entire effect. And you can see it's giving rise to, because excitations of harmonic oscillators are particles, that's you are finding entangled pairs of particles. You can get 0, 0, which means no particle here, no particle here, superposed with 1, 1, which means one particle here, one particle here, and so on. So this is very important to go back to these first principles, because a lot of the things which are being done these days, where people are saying maybe a black hole could do this, maybe it could do this, maybe you have a code space, subspace here which looks semi-classical. It turns out that in all of those cases, people have not actually gone back and seen what are the restrictions imposed upon you by the Hawking process. So anything which mimics semi-classical physics, let's say a scalar field satisfying the free wave equation to any approximation. So here's the approximation. You cannot actually stop these pair creations from happening. And you have every time you say that in some way you've got a semi-classical approximation coming out at the horizon, you've got to come back and see, is this actually working? And in many of these papers, you find people have not gone and checked that. So actually they don't have a smooth horizon while they are thinking that they might have.
Sorry,
okay,
a question about the slide.
Yes, please.
Just maybe a couple. One is, you're doing QFT in a fixed background here, but if you want to really compute entanglement entropy in a gravitational theory, there's this problem that the Hilbert space isn't factorized. So for you, are you going to say that problem isn't going to affect this description of the entangled pairs that lead to the paradox, or? Like...
Yeah, so it will not affect anything. So the point is that once this B moves far out, the Hilbert space does factorize to whatever approximation you need, because once quanta are in your room, in your hand, they are factorized from things far away. People have made a big fuss about the fact that in gravity, things are, bits here may not be independent of bits there. It's actually not correct. If you try to, whatever you try to do with it, if you try to make any small entanglements, you will see the small correction theorem takes care of it. It doesn't remove the problem of growing entanglement. If you make effects which are large, you will see things which are in conflict with what is in the lab. So people make a big fuss about things not being independent degrees of freedom here and there in gravity. It's actually not true. But we can have a full discussion about it later. Absolutely. It's very relevant.
And the other question is, you mentioned this, when the slices stretch, the oscillators decouple and you get this entangled state. I'm a little bit confused. Are you saying that the state wasn't entangled before the stretching? Like if you just have, what is the relevance of the stretching here?
So let's see what I was saying was entangled. So here the state was in the vacuum because they're two coupled harmonic oscillators, right? And the whole state is in the vacuum. So it's the vacuum of two coupled oscillators. Okay, so it involves both the oscillators in some complicated way, and that's fine. Once the oscillators have split, like this quantum B has gone far out and C is inside. I should run the other way around. B is outside and C is inside. When they are far away, there's no coupling because the coupling comes from the grad phi square term in the Lagrangian, and the grad phi is phi at 0.2 minus phi at 0.1 upon distance, and the distance has increased, so that's why the coupling is gone. Right? So you can just read this off from Hawking's calculation. Once the coupling has gone, now you want to describe local particles. If you're far away here, the local particles are given by the local oscillators there, and now I'm trying to rewrite things in terms of the local basis. And in terms of local basis, the same state would look like having some 0 here times 0 here, but also 1 here times 1 here. So if you write the ground state of the coupled oscillator in terms of ground states of the individual oscillators, these are the natural particle modes here. These are the natural particles separately, natural particle modes here. You'll find the vacuum here is not the vacuum in this language. This is just writing the essence of Hawking's calculation in a toy way.
I see. Thank you.
Okay, so this is the picture. The pairs come, then the slices stretch more. The older member of the pair goes here, the outer member goes here, then a new pair comes in between. And so you keep getting more and more pairs outside, and their partners go inside. As we said, it's not important to say there are two particles, two pairs and three pairs. You can just keep 0, 0 plus 1, 1. And this is a toy model of the entanglement. And this has all the structure we need to understand Hawking's puzzle. So here's the summary so far of what I have said. You can't stop yourself from making a black hole. Once you make the black hole, get entangled pairs, and then the entanglement of the outside with the inside keeps rising. And then near the end of the evaporation process, what do you do? Well, how does it all differ from normal bodies? Even a normal piece of coal radiates away and there is no puzzle. But for example, here's an atom in the piece of coal. It may emit a photon, And when the photon goes out, it does get entangled with the atom left behind. Suppose the photon went out as spin up, then the atom may be left behind with spin down. And then to that, you have to add the possibility the photon went out with spin down and left the atom with spin up. So the entanglement of the photons with the remaining coal does keep rising in the beginning. But after some time, if you want the coal to completely evaporate away, this atom left behind also floats out as a piece of ash, let's say. And then this atom and this are entangled with each other, but not with anything left behind. So in the end, when the coal disappears, each photon is entangled with its own piece of ash, and all the radiation has complicated entanglements with each other, but there's nothing wrong with this being left with a vacuum. So after the halfway point, the entanglement actually starts coming down. And in the end, the entanglement of the outside of the faraway region with what was inside has actually gone to zero. That's called the page curve, the curve of a normal body, and there's no puzzle. The real source of the problem here is the entanglement doesn't ever come down, it keeps going up. Because as long as the black hole is radiating, the new pairs are actually coming out from the vacuum. So it's not like anything inside ever comes out. These guys actually keep staying in there. And as we had seen, that's what the structure of a black hole is. So this is why the whole problem is there. This is the graph for a black hole. This is the graph for a normal body. And that's the actual information puzzle. Okay, so what's the solution? So a lot of people have worked on trying to understand the solution to this puzzle. I just listed some of the people who have put in very hard work in here. And what I'm saying now is a sort of summary of what everybody in that slide has been doing. So if you come to string theory, it's at least a perfectly consistent theory of quantum gravity, maybe the only consistent theory that we know. In that, if you want to make a black hole, you have to take a bound state of all the fundamental objects in the theory, which are gravitons, strings, branes, and so on. You'll compactify some dimensions. For example, your 9 plus 1 dimensional space, you could compactify it on a T4 and an S1, or maybe a K3 and an S1. And this is the non-compact spacetime, which is then left over. You compactify these dimensions because then on the compact dimensions, you can wrap certain objects. For example, if you had a string, a D1 brane, you could wrap it on, this should say D1, I'm sorry, it just says D. On the D1 brane, you could wrap it on this S1. And then from the point of view of the non-compact dimensions, it would look like a heavy point mass sitting at that particular location. You could take D5 branes and wrap them on a T4 cross S1 or K3 cross S1. I've drawn them in green here. Again, this should say D5. You could take N1 of these, N5 of these, trying to make a bound state. You could just take gravitons and make them run, let's say, around the S1. They carry momentum mode, so we call it, they carry momentum in that compact direction. We call the momentum modes P. You could take NP of them. And the bound state of all of these would look like a localized object from the point of view of the non-compact dimensions. To make a black hole, people realized that at some point, they take a bound state of 2 or more of these kinds of charges. If you just take one kind of charge, you don't get a black hole, but 2 or more, you get a black hole. And then you can start computing the entropies of those. And if you have N1 of one kind of brane, N2 of the other kind of brane, the entropy goes like the product, N1, N2, and then you take a square root. So if you take the winding charge of the string and the momentum, I've drawn it like this in a cartoon, wrapped in the compact direction, N1 units of winding, NP units of momentum. Well, that from the non-compact dimensions point of view will look like a heavy mass sitting at one place, carrying these charges. And then you can also compute the entropy of taking 3 kinds of charges together. So you could take all these D1 branes, D5 branes, the momentum modes. The momentum modes are now drawn with these blue arrows. The D1 branes are drawn as these red strings, and the D5 branes are drawn by these green whatever boxes. These are D5 branes. It's just a cartoon, but then the entropy again goes as N1, N2, N3 square root. So people started realizing that pretty much all the black holes they want to make, they all have similar entropy formulae. You multiply the numbers of different kinds of branes, and in the end you take a square root. The remarkable discovery of Strominger-Waffer from 96 was that if you take this particular black hole with these branes, if you take the mass and charges of those branes, instead of counting the entropy of these brane bound state, which is what they did here, if you actually just try to make a black hole carrying that much mass and charge in standard classical supergravity, well, then you find that you actually get a space-time, it's flat far away, then you get some kind of a neck, and then inside there is a horizon. And if you measure the horizon area, and you compute the Beckstein entropy of coming from that horizon area, A by 4G, you get exactly the answer that you got from counting how many bound states you could make by taking those 2 different branes together. And later, the same kind of thing was done also for the 2-charge extremal case, centered an approximate calculation, and double because, you could get the Beckstein walled entropy, that's A by 2G in that case, but the same idea basically kept working. So I keep mentioning this 2-charge black hole as well, because once we start studying the black holes, it's easier to start with the 2-charge black hole and then try to move on to the 3-charge black hole. So here, what we learned from this is that string theory is telling us something very interesting about black holes, because this is the first time that people could see that the entropy which comes from the horizon of a black hole, which is a very simple thermodynamic argument, that's exactly matched by a microscopic count of states, which you can just learn from putting strings and brains together. So similar things also extrapolate to near extremal and far from extremal black holes. This time you have to use brains and anti-brains. I've called anti-brains by n bars. But so if you do now, you draw the momentum going up and momentum going down. So you can call it P and P bar, NP and NP bar. And then these up and down guys can also collide and they can come off. Just like if you have vibrations on a guitar string coming both ways, they can collide and come out into the room like sound waves. And this like gives you the radiation rate from there. And the radiation rate from these, it actually agreed with the Hawking radiation rate. So in fact, the entropy is working, the Hawking radiation rates are working from near extremal states. But there's still a problem. Firstly, it's not clear what the entropy of the microscopic thing is counting in the gravity picture, because in the gravity picture, you just see the vacuum at the horizon. So what are you really counting in the microscopic picture? The microscopic picture calculation you can think of, at least for these non-extremal things, as some kind of a weak coupling picture. So at weak coupling, you just have all these strings and brains. A strong coupling, just see the horizon, and you take its area following the old arguments of Bekenstein, and the numbers are agreeing, but there's nothing to count on the gravity side. But somebody could still say all those, that entropy is hiding at the center at r equal to 0. But the other problem is much more serious. If the emission from the horizon is still going to happen by Hawking's process, because we have seen we don't know how to stop it, well, then you still have the growing entanglement problem. But in the weak coupling picture, you were just radiating energy from a string. There was no problem there. It's like a piece of coal. But in the picture with the horizon, you still have the same problem. So we haven't solved the information puzzle, but it does seem that string theory is going in the right direction as far as black holes are concerned. So what should we be doing? We should actually be taking these brains, trying to make their bound state, and study the wave function of the bound state, add strong coupling, and ask, do we really get this horizon? If we do, then we still have a problem. So as I said, take the bound state of these guys, and let's use the same charges that we used in the Strominger-Waffe black hole, D1, D5, and P charges. At weak coupling, if you make the bound state, the size of the bound state might be string length or Planck length, something small like that. And the idea was that at strong coupling, that size may remain like Planck length, some kind of little Planck mesh there, but its big horizon will develop around it. If you take a large number of brains, the horizon can be of some classical size of a black hole, and that's the guy whose area we were measuring. But that's why we had the Hawking problem around that horizon as well. But in fact, when we tried to estimate the size of this bound state, we found that wasn't the case. The size of the bound state actually increased with the number of charges. The size of the bound state, this diameter d here, increased with the number of charges. It also increased with the string coupling. Here, V and L are the volume of the T4 and the length of the S1. So they just have something with the compactification. But all these 7 parameters in here for the size estimate of the bound state come in just the same combination, which gives the Schwarzschild radius of that particular black hole. So that's very interesting. It's only an estimate of the size, and anybody could say we don't believe estimates, they are too crude. But the fact that to give the same expression as the horizon radius, it suggests that perhaps in string theory, the size of a bound state always grows with the number of quanta in the bound state in such a way that a horizon never forms. And if that is the case, of course, there's not going to be any information puzzle. The black hole will be like a piece of coal. This is the idea which these days is called the Fuzzball conjecture. Of course, this was only an initial estimate. And then people said, let's go back and start actually making these states one by one and seeing if that's actually the case. So as we said, the simplest case was where we take 2 charges and take the extremal holes. We call it a 2-charge extremal hole. By using dualities, you can take those 2 charges to be any 2 charges. You could take the string winding, which we draw here, and the momentum, or you could use D1 brains and D5 brains, any 2 of those you could take out of the 3. So here, let's say there are n more units of string winding, but you have to make a bound state. If you bind many strings which are wrapped on a circle, the bound state is very simple. You just take the string, you wrap it n1 times, and then glue it back to itself. You might as well open up to the covering space, and there it has something. If the length of the compact circle was L, it opens up to a total length L total equal to n1 times L. Well, the momentum is also to be glued onto the string because you want a bound state. So you have to ask, what happens when you glue momentum onto a bound state? Well, it has to carry the momentum as traveling waves on the string. So all you get is a string carrying traveling waves. And now here comes the important point. If you take an elementary string, it has no longitudinal vibration modes. It only has transverse vibration modes. So if you want to carry any momentum on it, you have to bend the string either to the left or to the right. And there you can see it's bending like this. And so different states will have different vibration profiles. And when you count all the vibration profiles, you get the entropy. That's how the microscopic entropy was counted by Sen for this particular case. Well, then can we actually find the metric produced by this? Again, if the string was carrying the momentum as longitudinal vibrations, everything would be spherically symmetric around it. You'd get a point singularity and you get a spherically symmetric solution, which might have a small horizon depending on whether you take stringy corrections or not. But on the other hand, what you really have is something which is not spherically symmetric. It has all these distortions. And when you actually have to compute the metric produced by this, you realize that This L was the actual physical size of the compact direction S1. Here we just open up to its covering space. But in the actual physical space, you can see what is happening. This piece of the string gives a little strand here. This piece of string gives a little strand here. So you get something like kind of a slinky, which sort of winds all around, but it's spread out all over the place because of these transverse excitations. So you get something more like this. The string source is spread all over here. And in fact, with that, you can then actually find the metric. The shape of the actual numbers here don't have to mean anything. I'm just giving them here for completeness. We don't have to use it for anything. If you give the profile as a function f, you define these functions in terms of f. Here's the f coming in as profile functions. You put them in this metric. You find the metric produced by each of the states that come out as a microstate of the two-charge system. So we could count all these states by using these abstract counting methods, but now we can actually construct them. And when you see what the states are doing, you find none of them actually have a horizon. Okay. And then if you don't have a horizon, this whole Beckstein idea of area upon G giving the entropy ever work out? Well, something very interesting happens. If you look at the size of the region where this thing was a mess, here they were all the same, but where they start differing from each other. And if you take the boundary area of the surface here and divide by G, that gives you the order of the entropy. It is of the order of the microscopic entropy in there. So the area thing is still is hiding in there, but there's no horizon, there's no singularity. The important thing is none of the microstates are spherically symmetric. So the mistake we were making before was we imposed the fact that in gravity we want a spherically symmetric ansatz because it was easy to solve. If you solve it with that, you find a horizon. Inside that you find a singularity. Now singularity is bad anyway. If you get a solution to a singularity, it may not actually exist in the full theory. What we're finding here is, in fact, it doesn't. None of the actual solutions are spherically symmetric because there's no way to actually add momentum to a string. That's going to be carried by transverse waves. There's no way to add momentum and to keep the whole thing spherically symmetric. So if the original black hole solution disappears, it's not there in the theory at all. All the solutions can actually be found. We know there are no other solutions because we started from first principles. People have done a semi-classical quantization of the space of all these solutions and reproduce the exact entropy as well. Beautiful work by Richko. So we understand everything about a two-charge black hole inside and out. And to the extent this was the simplest toy model of a black hole, we know that all the states are actually fuzzballs. You can dualize them to get D1, D5 states. This time there's no momentum. But if you have D5 branes and D1 branes, sort of looks like this. These things give you the spins of these D1 branes. They're just technical things in there. If you now want to add the momentum, they're carried by these momentum modes. If you want to add go non-extremal, you have to add momentum and anti-momentum. You have momentum going one way, momentum going the other way. And for many of these three-charge things also, so all these two-charge things are known. So all the by duality, all these two-charge things are known. But for the three-charge, people have done many, many families. Very beautiful work by Bina, Warner, Martinek, their collaborators, and so on. And they have found lots and lots of families. In each case, when they try to find the structure of the gravity solution at strong coupling, they find a fuzzball. You have flat space far away, then some kind of a neck. But instead of a horizon there, you get this kind of a mess, and they actually compute what structure you get for that particular state. So all the no-head theorems, actually, they found this beautiful paper of Gibbons and Warner were bypassed by the special properties of string theory. And in general, what you find for all these solutions is that the compact dimensions in the gravity solution are not trivially factored. They're not trivially tensored with the non-compact dimension. So that's the mistake people were making in the past when they couldn't find any here. If you take a solution in, let's say, 3+1 non-compact dimensions or 4+1 non-compact dimensions, they would take the extra compact dimensions and say, well, the black hole is very big. The extra compact dimensions are like Planck size. Let's just factor them out and try to write a solution in 3+1 dimensions. Doesn't matter what you do from that point on, you will get a spherically symmetric solution only. You will find the horizon, you will find a singularity, and you will have the information paradox. But when you actually take the solutions in string theory from scratch, the bound states, and you see what they look like at strong coupling, it takes, the technology is advanced to the point that we can see those wave functionals. You find another solution that's spherically symmetric, but what's actually happening is the compact dimensions are not trivially tensored with the non-compact ones. So the compact circle may come and just get pinched off somewhere, may create a closure-Klein monopole, somewhere else it makes an anti-monopole, there's an S2 between them, there are fluxes on it, they're all kinds of structures, but the compact dimensions are not trivially fibered over the non-compact dimensions locally. So the total net charge of there is zero, because from infinity they are tensored, but inside the two are not factored. So we just draw the fuzzball, this whole messy region. I won't keep drawing this entire picture. The whole thing has become more like a piece of code with all this structure, and many, many examples now, we know the explicit structure here. So as we said, if you want all the states of the Strominger of a black hole, you have just got to look at all the possible ways of putting these D1 branes into different twist sectors, as we call it. You can break some strings wound like this, some broke into other pieces. You can put different amount of momentum and anti-momentum on them, and all the states are here. Well, for lots of subfamilies, I say all the 2-charge states, but then special families of 3-charge, some with near extremal, like non-extremal, like some going up and down. So many different examples have been constructed, and they've all turned out to be fuzzballs. So this would actually seem pretty convincing, and to a lot of people it was, that in string theory, the bound state always fills up to the size of the horizon. There is no smooth horizon. There is no puzzle. But some people were still worried. Some people, in fact, in the string community were saying, no, perhaps all the ones which are far from extremal, which we haven't been able to construct because the near extremal ones are always easier to construct, perhaps these could still have a smooth horizon, and all the ones you have constructed which are extremal or near extremal might just be special cases. Well, why would anybody say that? It doesn't look logical that if all the ones you could construct were like pieces of coal and that solves the puzzle, why would people want the ones far from extremal, like the Schwarzschild black hole, which have no charges? Why would that still have a smooth horizon? If it does have a smooth horizon, how would they solve the puzzle then? And the reason was that they had a belief in something called the small correction idea. So what is this belief? The belief is that Hawking did a leading order calculation, and there you can see the particle that went outside is entangled with the particle which stayed behind, right? So that's what was giving rise to the entanglement. But there could be subleading corrections that Hawking didn't take into account because they come from some effect of quantum gravity we don't know. And then that may introduce little correlations between every particle and every other particle. Now, these correlations had to be small because they're from some subtle quantum gravity effects, and we are still keeping the vacuum at the horizon to leading order. We just some subtle quantum gravity effects. The correction is very small. But why would a small correction matter? It would matter because the number of particles you emit is very large. A black hole of mass m emits m over m Planck whole square particles before it's done. So because suppose the correction was 1% at each emission, but there were 100 particles emitted, then in fact, perhaps when you compute the entanglement of all these 100 outside guys with all the 100 inside guys, these small corrections accumulate and make the entanglement become 0. In that case, what is inside can disappear, and these guys are not entangled. They have a pure state, and there is no puzzle. So one way or the other, this belief, which is actually incorrect, as we will see, has underlined all the opposition to the fuzzball paradigm. It has kept coming back in different forms because on the face of it, it sounds so persuasive. And in fact, when Hawking retracted his original claim of 1975 very publicly in 2004, saying that some instant-on effects coming from other topologies in the black hole might get rid of the information problem, he was really actually talking about the same kind of idea based on an earlier paper of Maldacena from 2000, that subleading instants may give exponentially small corrections, but then those may, when brought back to Lorentzian section, actually give you these entanglements and take care of the puzzle. So let's just see more, because idea has been so prevalent and it has been wrong. Let's just see what the idea is a little bit more explicitly. So suppose at the first step of emission, you emit B1 and C1. B1 is outside, C1 is inside. And suppose you do the normal emission, 0, 0, plus 1, 1. At the second step of emission, let's try to correlate that with the first step a little bit. Let's suppose at the first step you emitted 0, 0. So you had 0, B1, 0, C1. Then at the next step of emission, when you try to make B2, C2, instead of making B2, C2, 0, 0, plus 1, 1, let's have a little bit more of 0, 0, little bit less of 1, 1. Okay, so now you can see the first particle is influencing the second particle because the first pair was actually had a 1, 1 instead. We'll make the corrections different. We'll make epsilon 1 prime. Let's change it a little bit. Okay, so now you can see we've introduced correlations, and all these terms proportional to the epsilon. The epsilon has to be small because to leading order it has to look like semi-classical physics Hawking at the horizon. But the number of these correction terms, if you correct all the terms which have an epsilon in them, after n steps of emission, there are 2 to the n correction terms. And so you might think that when you emit a large number of particles, a solar mass black hole emits 10 to the 120 particles before it's done. So if you take that many particles coming out, then in a leading order, you would have gotten this. But after taking into account of small corrections, maybe the entanglement actually goes down. If that were true, there was no Hawking puzzle in the first place. Hawking did a leading order calculation, and he was just wrong. But in fact, the small correction theorem actually showed, it proved in this thing here, that such a resolution is not possible. And here's the theorem. The correction to the state, at each step, let the correction be this. This was the leading order answer. We'll add a small piece. This is the low energy small correction. And let's say the norm of this is bounded by epsilon, but this delta psi k is different at every emission step. Okay. We also assume that once the radiate quantum has gone sufficiently far from the hole, well, then we won't change its state. Now that's also true for a piece of core, right? Once a photon comes out, once it goes, suppose a piece of core is this big, once it's, let's say, 10 meters, 1 kilometer, 10 kilometers, some distance away, its state won't change anymore. So let's assume that. This is a technical thing. The vacuum is unique. Always assume that in quantum field theory. Then you can prove that if these corrections at each step are bounded by epsilon, it doesn't matter how many particles you emit, the entanglement at step n plus 1 will be greater than the entanglement at step n plus log 2. This is the leading order Hawking calculation. The maximum reduction you can get is minus 2 epsilon. Okay, so if the leading order answer vector was this, the subleading answer also keeps growing. You can't actually make the thing turn over. So no small correction at the horizon can ever fix the problem. If you want to fix the problem, you have to do an order unity correction. And when you actually go to string theory and you actually see what's going on, you find the order unity correction because you get these fuzzballs. So in that sense, you would now say that everything is done. Why were people so confused about a small correction issue? And the reason is that this is actually extremely non-intuitive because it actually, the proof relies on the strong symmetry property of quantum entanglement entropy, which is a behavior of how four systems actually entangle with each other, A, B, C, and then there's a fourth path, D. A, B, and C actually enter the inequality, but if D is not there, thing becomes trivial. So it's a very complicated theorem to prove because the proof of it is not elementary. So it takes 10 pages to prove this. And so because this relies on that particular theorem, the proof itself is not long on the physics side, but because it relies on this somewhat intricate theorem from quantum entanglement entropy theory, it's not intuitively obvious to people. And that's why people kept thinking that maybe the small corrections will take care of it. So again, also to summarize where we are in the traditional picture, the black hole had basically a vacuum at the horizon. So the state at the horizon is overlap with the vacuum was almost 1, close to the vacuum. And you got these pair productions, smaller or epsilon. With this, you cannot solve the puzzle. With the fuzzball, the state here is nowhere close to the vacuum. The overlap will be very close to 0, and you get nothing like the pair production, just like a normal body, and you then solve the puzzle. Okay, so now our picture has improved because now with this, all these limits, extremal, near extremal, we have explored so many of those that there's no room left in there. And then if you go far from extremal, well, all those black holes anyway Hawking radiate. Extremal black holes don't radiate, but all other black holes do. And then for them, if you don't actually have a fuzzball structure, if you have any approximation to a smooth horizon, you cannot get unitarity. So if not fuzzball, then cannot get, should say unitarity. Sorry, not fuzzball, then cannot get unitarity. Okay, so you would think that would be the end of it. So actually, I really thought that this would be the end of it, and there would be no other complaints about the fuzzball paradigm. But some people were still opposed to the fuzzball paradigm, and let's see what the opposition was this time. Then people say, okay, let's agree the black hole is not close to the semi-classical picture in the full theory. It's actually some very messy object like a fuzzball in the exact quantum theory. We'll draw the messy object like this. Could be a fuzzball, we don't even care what it is. Let's just say it's some kind of mess. And because it's a mess, it radiates from its surface like a normal piece of coal, and so there's no information puzzle. So these people will not go and try to prove that. They'll not try to show you how you actually got the structure. They're not even using string theory. They'll use very simple arguments like 2D gravity, JT gravity, and so on. They'll say, let's just assume that happened for some reason. It could well be a fuzzball. But then once this is done, there's no puzzle, of course, now, because we've assumed the whole thing is like a piece of coal because some effects we don't know. But now let's think that there will be some small thing, subspace of the entire quantum gravity space here, which we call a code subspace, the small subspace of all the quantum gravity degrees of freedom, subspace of the exact things, which will reproduce a good approximation to low energy semi-classical dynamics. These are the wave functions, empty vacuum here, wave functions of B and C quanta, all the Hawking stuff that we said. So in this view, fuzzballs are not wrong. The real thing is the fuzzball, you've done all the work, you found them, good, you solved the puzzle, but it's not a useful way of thinking about anything because the real dynamics, you should look at a semi-classical approximation. You see this, and this is what you will see if you try to probe it at low energies. And so why not just look at the black hole like this? Why go to all this mess? What could you possibly learn from that? But it turns out this picture is wrong. A and B are not compatible. If in the exact theory you want the entanglement to come down, there's actually no code subspace where you could get an approximation to the semi-classical theory. So this is what we proved in this recent paper called the effective small corrections theorem. And I'll tell you an exact statement of what is not possible. But you can see where the trouble will come from before we even start. If there is some approximate to pair production, then with that approximation, the entanglement will keep rising. But once something reaches infinity, at infinity, there's no approximation or anything. Every particle is just a particle. You can measure it to as much accuracy as you want. And then you'll actually have a problem with growing entanglement. So the following, for example, is just a concrete statement. Then we can see how we want to use it. Let's make a concrete set of assumptions and see what we get. As we said, let the exact description of the black hole be some very complicated mess. All the region up to 4m. The horizon is 2m, but all this region, let's say there's some quantum gravity, we don't know what's going on. All we assume is the dynamics in this region is unitary. Okay? We're not assuming it's close to semi-classical. And far from the whole, let's say beyond 100m or something, it's just normal local flat space physics, like you can see in a textbook on string theory. You have gravitons, you have strings, nothing else. Now from the exact degrees of freedom, we make some effective degrees of freedom, which are some function of the exact degree of freedom, just extract a few complicated linear combinations. And then from those, the Lagrangian will have to follow, all quantities will have to follow. But then with that approximation, by recoding these bits into this small subspace, suppose you get effective description, an approximate description of a scalar field. We will not ask for much out of this approximate description. But in this approximate description, you'll have the pair of entangled modes. That you can't stop because you've got an approximate to semi-classical physics. You'll be forced to get the creation of entangled pairs, but we ask for very little. We ask that the effective field description works only at long wavelengths. Let's say bigger than 1 Fermi, that's like the lab, 1 Fermi nuclear physics. We won't, for example, ask for it to work at Planck scales. This box phi equal to 0 scalar field, we assume it only works to some approximation. It doesn't have to be exact. We don't even assume that this map, which gave us the effective degrees of freedom, work for all times. It could work for producing, let's say, 100 quanta, after which some other map may give us the next 100 quanta. Okay, so everything we have given in some way, let's see if we can get semi-classical physics around the horizon. So in the exact theory, some mess comes out of here and goes out. In the semi-classical approximation, some pairs like this come out. But at infinity, everything just has to become gravitons. And again, these will be slightly different from these because this was the exact theory, this was an approximation. We've done exactly what you might want. With this, the effective small correction, which is a small extension of the small correction theorem, it proves that in this exact theory, if it has that semi-classical approximation, the entanglement will actually have to keep rising. It can't come down. What does this mean? What did I just say in these last slides? It means that the following belief is false. If there's some kind of exact theory where the thing behaves like a piece of coal, there's no approximation to it, but it also looks like a semi-classical physics in some code subspace. So I just mentioned that because a lot of the people these days keep mentioning the fact the actual black hole is like a piece of coal and the page curve comes down, but Hawking made the mistake of using a semi-classical approximation, and that of course it goes up. But it's back to the small corrections error. If there's some code subspace in which the thing goes up, it's not actually going to work. Then the exact theory, it comes down. There are various modifications of this scenario, but they all run into trouble. And in this paper, it's sort of a long paper for that reason. They're like, it's an 80-page paper, but we went through all of these different scenarios, about 7 or 8 different scenarios that people do, modification of this in different ways, but they all run into trouble. Some had no unitary evolution here. In some the page curve didn't come down, in some the horizon wasn't smooth, and so on. So you can look at this paper for all the different ways that they got into trouble. But given that they're having so much trouble, where does this idea actually come from in the first place that things should be a mess, but it should really look smooth in some effective language? Why are people trying to push that so hard when it's not working? And the origin of that desire comes from an incorrect extension of the idea of ADS-CFT duality. So let me just take this slide to introduce ADS-CFT duality to those who are not familiar with it. But the idea is just this. You take some collection of D branes, let's say D3 branes in string theory, and suppose a closed string drawn by this red loop falls onto it. When the closed string falls onto it, it excites the D3 branes, makes vibrations of them, which you describe by little open strings that run between the D branes. So the closed string breaks some little open strings, and they make a mess over here. And as time passes, these open strings are spread out along the D branes, and that's the further evolution. What Malthus observed was, well, that's certainly a very complicated evolution, and you could put this in a computer and do it if you really wanted to. But there's an equivalent description where you replace these D branes by empty spacetime with an ADS geometry. And this closed string, instead of actually breaking into this awful mess and the mess spreading, whatever dynamics that was, can be mapped one-to-one onto the dynamics of the string just falling deep into the ADS throat completely smoothly with nothing bad happening. So all the oscillations of the closed strings were going like a clock, was actually encoded in this complicated dynamics, but some other way, in this gravitational variables, which are complicated combinations of these Yang-Mills variables, it just looks like smooth empty space. Well, that's very beautiful. So why not use the same idea here, that the actual black hole is very messy, and if out of that, in some way, there's some effective degrees of freedom, so that messy description would be like this open string mess, but then there's these closed string kind of description, so it just looks like falling through empty space. Why can't we have that? But now looking at the slide, you can see where the difference is. In the D3 branes, you start with the D3 branes in the ground state, which is actually the vacuum. So there was a unique state over here. And in the ADS also, you're falling through a vacuum region. So the vacuum here can be mapped to the vacuum here, and there's a nice, beautiful map. That's not the case here. There are many different states of the black hole because the black hole has a big entropy. You can't map them onto one state, the vacuum. That's the beginning and end of the problem, because if you want the information to come out, you have to see the difference between different states, and every quantum Hawking radiation that comes out has to see the difference between different states. If you replace them by one common state, it's not going to work. And that's what you're seeing again and again through all these small correction theorems. So the incorrect extrapolation of ADS CFT is, ADS CFT works beautifully when the CFT thing started in a vacuum before being excited, and the corresponding gravity solution also was in the vacuum. But the idea of holography does not work at surfaces like the black hole horizon, which are defined by the amount of entropy they contain, because there are many states inside, and you can't map it to one state outside. But belief in this ADS CFT idea, trying to extrapolate that here, was running into this idea that this is why people are keeping on trying to get somehow this thing to work. But now we have seen that no, it can't work. The fuzzball is the beginning and end of the story. To solve the information paradox, it ends with a demonstration of fuzzball structure. The small correction theorem told us you didn't order unity correction to energy dynamics at the horizon, and the fuzzball structure gave such a correction. And the effective small correction theorem tells you there's no effective description, which makes it look back like a smooth thing. You'll always just have to stop here. So that's also the end of it. People have computed radiation from simple fuzzballs. It has the same rate expected for those simple cases as the Hawking rate, but the details are not the same. It's not coming out of pair creation. You can see the information of the black hole being imprinted onto this. So in very simple cases, all the radiation thing has also been worked out. It actually sees the whole structure of the thing and sees all the information imprinted on it. Again, these are for very simple black holes. You could always say we don't want for a Schwarzschild black hole, but I think there are too many different pieces of information which tell us no other picture is actually working. But there was yet another attempt to go around the fuzzball paradigm. What was this? This is the idea of wormholes. And this idea looks like the following. Again, the black hole horizon is somehow smooth, and it's in the vacuum state. But the entanglement between the black hole and the radiation is somehow creates wormholes in space that do something to resolve the Hawking puzzle. It was a proposal by Maltzer and Susskind from 2013. But this is very puzzling. Right on the face of it, because they didn't try to make it precise, but the moment you think a little bit about it, it's confusing for the following reason. What do these wormholes mean? Some people have said that these wormholes are only a depiction of the fact that the quanta are entangled. There's nothing really there. It's just a depiction of the fact two are entangled. But it's only a depiction of the entanglement. Then how can it solve the problem? The entanglement is there. Well, don't depict it that way. Then you haven't done anything. So the wormholes have to do something. If they have to do something to get the information out, and the wormholes come whenever two things are entangled. The idea was whenever two things are entangled, there's a wormhole between them. Well, then it actually conflicts with the linearity of quantum theory. Because suppose you take a state which is not entangled, 0b, 0c, between b and c it's not entangled. And suppose in quantum evolution, it evolves to a state psi1. Then you take 1b, 1c, again, this is not entangled. Suppose it evolves to a state psi2. By the linearity of quantum mechanics, the entangled state has to evolve to psi1 plus psi2. Entanglement never does anything. Once you know the dynamics of all the unentangled states, by linear superposition, you can find the dynamics of all the entangled states. How can entanglement make a wormhole and that wormhole do something for you to get the information out? This thing doesn't seem to make any sense. Even though this was the initial idea, and this criticism can be applied right to the initial paper, all the other things that people are doing with this actually is subject to the same problem. And so I just want to keep to this elementary idea and see where it goes. But where did this idea come from? It came from the idea that in ADS space, again, you have the dynamics of this ADS. It can be replaced by the dynamics of D3 branes, which are placed at the boundary of the ADS. So you either excite the closed string by the D3 branes at the boundary of ADS, or you take the D3 branes away from the boundary and let them fall into ADS. Well, if you take what's called the eternal black hole in ADS, it's a space-time which has a black hole on this side, a black hole on this side. If you haven't heard of the eternal black hole, that's fine. This part may not make any sense, but it's a space-time geometry which has two sides to it. One black hole exterior here, one black hole exterior here, and it's all connected. And people said, what's the dual to this? Well, since there are two boundaries, one on this side, one on this side, it seems that there should be two CFTs, one on this side, one on that side. And these two CFTs are not touching each other. If they're not touching, they're not interacting. The best they can do with each other is have a state which is entangled. And now this gives the idea that entanglement between two different theories leads to a physical connection, because at least in the dual description, the spacetime is connected over between these two sides. And here, the two things were just entangled. This gave rise to all these ideas that ER equals EPR and so on. Just means that somehow entanglement leads to physical connections. And this thing has led to all these ideas that somehow wormholes might come wherever there's entanglement, and spacetime does something very interesting and very funny. But there's some immediate difficulties with this entanglement, which were pointed out in this paper quite some years back. And the difficulties of the following kind. So first take the black hole picture down here. Here's the black hole. This is the black hole in ADS, but you can take the ADS boundary and couple it out to flat space on both sides. That's just so that I can sit at flat space. If something comes out, I can observe it. So give me time to observe it. If I send a particle in from here, it just crosses into the black hole, the middle line quite easily. And when these black holes evaporate, I can let both sides of the black hole evaporate. The Hawking radiation will send part of the information here, part of the Hawking radiation will go here. If the space-time is connected, it's impossible to stop the information from coming out partly here and partly here. But if I have two CFTs, now remove the space-time, replace the space-time by only the CFTs on the boundary, they're still connected to their flat space outside, and from this flat space outside, throw a particle in as before. It'll excite this particular CFT, but there's no way the information of this can actually come to the other side. If two things are entangled and you excite one guy, suppose this guy had spin up, the information, the fact this guy had spin up can be seen by what radiation comes out on this side. It can never be seen by doing any experiment on the other side. So similar things, and you can do many toy experiments like this, and there were 3 different contradictions shown in this paper. Somehow this thing doesn't make sense. You can actually make a contradiction to linearity of quantum mechanics right away. So the fact that diagonal can't do anything is of course a well-known fact. So why were people doing this? So what should the correct answer be? If you have 2 CFTs which are entangled, each CFT should just lead to like a state, every state is like a piece of coal. You should just get 2 entangled pieces of coal. There should be no physical connection. Why are people saying that you actually get a connected diagram? This happened because people started with the reverse question. Start with the eternal black hole diagram. Now that is connected. That has 2 boundaries. That's clear. And the 2 boundaries are not touching. They can at best be entangled. So how do you beat the idea that physical connection comes from entanglement? So just pose the problem here. This way it does look somewhat convincing. The error in this argument is the starting space-time that you have actually doesn't exist. So why doesn't it exist? It's because such a nice smooth space-time. It has singularities here and here, but at least if you start with a Cauchy slice here, it looks like a smooth space-time. But go back and ask, what happened to the original black hole? Well, that didn't exist either. We found that's actually been replaced by fuzzballs. Whatever took this away will take this away. There can be no approximation to this, as the small correction theorem tells us, because otherwise quantum mechanics breaks down. There can be no approximation to this. So the question is, what removes all these semi-classical geometries? That's the last part of what I want to say. So if I could just take a couple of minutes, I'll just tell you that, and then I'll stop. So this is what we call the breakdown of the semi-classical approximation. So if you take a shell which is collapsing, you follow its classical dynamics, it seems to go inside the horizon, seems to make a classical horizon. How does it ever turn into fuzzballs? All the dynamics look so classical because the black hole is so big. Well, when you look at the actual fuzzball structure, you find there's a path for quantum tunneling from the shell to the fuzzball. But the probability for tunneling, of course, is very small. Because if you take a very massive shell, a massive object tunnel to another massive object, the probability is going to be tiny. And that's true. The whole beauty of a black hole, though, is that a black hole has a very large entropy. So you don't just tunnel to one fuzzball, you tunnel to a large number of fuzzballs. And what's going to happen is the probability of tunneling is small, but you multiply by the number of possible final states, the number of things you can tunnel to, and that's very large. And this smallness will cancel the largeness. Here's the calculation which I won't go through, just to show that the 2 numbers agree, because I'm out of time. But the rough quantum mechanics analogy is this. If you hold a particle in a box, that's just a state. That's like the traditional black hole. And somebody says, it's there, I can see it. Why can't I have the traditional black hole? But the point is there are many alternative states there, which are all these fuzzball states, which we have now found in string theory are active solutions of the whole theory. Then if this state can tunnel into all of these, then in fact, this is not a good eigenstate. A superposition of all of these is the actual correct eigenstate, and this state here doesn't exist. It doesn't actually solve the equation h psi equals E psi, and for this black hole doesn't exist. The eternal black hole doesn't exist for the same reason. It actually immediately tunnels over into this factorized form. So all the ideas that are derived by using this black hole actually have the same puzzle that we had all along with the original black hole. If you assume the picture of the original black hole, the small correction theorem tells you, you will have the growing entanglement, you will lose unitarity. If you use the eternal black hole, use that to argue for the Einstein-Rosen bridge, ER equals EPR, any of these pictures will again get into contradictions. Okay, so here's my summary. All I have told you is Hawking pair creation leads to an entanglement problem. That's the problem. The small correction theorem makes it into a rigorous problem. Nothing close to this picture will ever work for you. It's just not understood, easy to grasp this theorem because it relies on something which is a non-trivial theorem to prove. The proof is very easy of this, but it relies on a theorem which is non-trivial to prove in quantum entanglement entropy. When you actually make McChrystal string theory, there's no problem because they all become these fuzzballs. And the actual original black hole geometry actually gets destabilized by tunneling into these large number of fuzzballs. And the recent ideas of ER equals EPR and so on, we find that none of them actually work. And this paper to come, we're actually going to go around and try to explain some of the things I have been saying. There are some fundamental reasons why they don't work. And those reasons are common to all the different attempts that people have made. So in my opinion, the Fuzzball paradigm remains a logical solution to the puzzle, and this puzzle has been therefore resolved. Let me stop here. Thank you.
Thank you very much for this wonderful talk. So any questions?
Yeah, I have a question. So I know you said that you're making some arguments based on the small correction theorem for why the more recent replica wormhole like calculations can't resolve the paradox. But I'm just confused. If I just take a particular calculation, like in 2D due to gravity, one can do a replica wormhole calculation of like the entropy of the radiation, and it looks like it does come. You do get the page curve, and I'm supposed I don't view that as some like it's purely Euclidean calculation that I do, just a path into a calculation. I don't view it as a calculation in which I actually know what the reduced density matrix of the radiation is. But just at a purely pathological point of view, I do the calculation, I see a page curve. So how does that, how does your objection sort of invalidate that calculation?
Yeah. So let me answer. That's very important because that's one of the things we spent quite some time in this paper explaining. That calculation is not correct. So there is no way you can take 2D gravity and actually show the page curve comes down. So I will tell you what the error in that calculation is. So with 2D gravity, if you just take 2D gravity, it has been solved a long time ago. For example, the CGHS model or the RST model, they solved the page curve, and the page curve keeps going up. Okay, that's from 1991, 92. You can just see those papers. So what are people doing now with 2D gravity, which makes them say that the page curve comes down? So what they do is they don't actually solve the problem in 2D gravity. What they're saying is the 2D gravity is not the correct theory. The correct theory is some complicated string theory or some other theory. And the 2D gravity theory, because it's an effective theory, I can make new rules for it. But the new rules they make, one of the rules is the fact that there should be a wormhole between different replicas. It turns out there is no such connection between different replicas. That particular path, there's no actual path in the full quantum gravity path integral that connects different replicas. The words used for that, justifying that, were the fact that in the CGHS model, people did not take into account topology change. And if you take into account topology change, you will find a replica wormhole. It's not true. If you take, it's true that CGHS did not worry about topology change, but what's topology change? If you, let's say, take CGHS model is 1 + 1 gravity, let's stick to that for the moment. You can do any other case if you want. Topology change means you can break the line into 2 segments. You can join it back again, you can break it into 3 segments, join it back. That's topology change. 2D gravity, let's say, with topology change, is just worldsheet string theory. We have been doing that for ages. Okay, so we know what topology change does. If you go back to how the entanglement entropy is obtained as a limit of Rényi entropies, you can go and see, you write the full exact thing first, saddle points will come later. There's actually no path that connects one replica to the other. Inside each particular replica, you will have handles coming from this breaking and joining. There's no connection from one replica to the other. So if you go back and see what they're computing, if you first compute Rényi entropies, which is what they do, and then take a limit to get entanglement entropy, which is what they do, the problem is that the Rényi entropy itself, when they write down the object which they call the Rényi entropy, is defined as trace rho to the n. That's the Rényi entropy, the nth Rényi entropy. Then you take the log and divide by a number. But what they do is they don't take trace, let's say, trace rho square. They replace trace rho square by trace rho square plus trace rho whole square. They say the extra piece is because some topology change. You go back to first principle and you ask what in the gravity theory gives you that term, and you find you don't get such a term. If you actually forcibly write trace rho square plus trace rho whole square, what you end up doing is finding the Gibbons-Hawking entropy. And so the argument becomes completely empty. If somebody were to say the black hole entropy is given by Gibbons-Hawking, then he wasn't saying anything in the first place. You already know the entropy is equal to the area. As the black hole shrinks, the area is going to 0, entropy is going to 0. It's like a piece of code, right? So there is no way to actually set up a path integral that gives you the Rényi entropy for an arbitrary state, which will actually come from a path integral of the kind they write. So I'm happy to go over that in detail with you by going over the slides, the pieces of our paper. But what they compute is not the Rényi entropy. The replica wormhole doesn't exist, and that calculation I think is empty.
But I'm a bit confused. So are they not allowed to just define a gravitational path integral where they say the measure in this path integral includes the wormholes when you look at the replicas? What prevents you from defining
they are not allowed. They are not allowed. And the reason is this. This is exactly what they have not done. The point is, if you make some effective degrees of freedom from the exact degrees of freedom, that's up to you. You can define any effective thing, right? G effective is a function of F exact. You choose them. They don't tell you what it is, but that's fine. They say it's complicated. They don't know how to do it. But after that, the dynamics is not up to you. Whatever the exact dynamics was, if you make this map, it will give you the Lagrangian for the approximate dynamics, right? And any quantity that's defined for the exact thing, it will force upon you what its form will be for the approximate dynamics. This is just a fact. The point is, if you say that I have made this approximation, and now in the effective thing, I can do whatever I want, because who knows what happens? That's where the problem is. If in the effective dynamics, you say there's a connection between replicas, you will find there's a connection between replicas in the exact dynamics. You try to write down what you could possibly do in a theory with, let's say, gravity. We can break topology, do this, break topology any amount you want. Show me how you get a connection between replicas. There's just no element in the path integral that connects to replicas, because replica is just a trick. It means you take one part of copy of a system, you take another copy of a system, and you sum everything. Don't take saddle point or anything right now. First write the exact thing, then we'll take saddle points. Assume you're going to put in a computer, you'll find no connection between replicas. That's the problem. They say, I can put whatever I want because it's a saddle point Euclidean. Why can't I do what I want? There's just nothing like that there. You're actually just computing Gibbons-Hawking. So if you have to make this connection, how the Lagrangian dynamics come out of the map? I think there's no such map.
Are you assuming there's some local, like the F of G exact is that G exact and G effective are locally related? I mean, I'm just wondering, how do you know that we can have a theory where the low energy theory has a sum of a topology, but in the exact theory, that sum of a topology is not there?
So I'm actually happy to have some more topologies in both theories, right? That's not my problem right now. But I'm saying by local, I'm not using any local. I'm saying anything which happens in this region all the way up to 4M, 10M, whatever you want, that's not local to here. There's such a quantum measure, not in any locality. Anything you do with degrees of freedom when you make these effective variables, it's not going to work. There's sometimes these people try to use variables here at infinity and variables here to make the semi-classical variables. We go through those kinds of possibilities, all of them in some detail in this paper we wrote. None of them work either. So we've tried all these possibilities, right? They try to make this, I'm not going to make it locally here. Do anything you want here. I'm even making the non-local ones from here to here. None of them work out. So I think you can't just say, I'll take 2D gravity, make whatever rules I want, get whatever answer I want, and keep going. That makes no sense. You've got to go back and see, at least give me a picture of what's going on here. You may not get the exact map, but say what kind of topology change in the exact theory is going to give me a connection between replicas and my approximate theory. Just show me that, and then we'll be on the same page.
I see. Thank you.
So since we're out of time, so let's end the colloquium here. Please feel free to stay around to have informal discussions. So let's thank Samir again for this very interesting talk.